Can you see?
Yes, I can see the slide. Can everybody see the slide?
Yes.
Okay. Okay. Hello, everyone. Thanks for coming here. Let me introduce myself first. My name is Qiu Jing. Now I'm working at T-Head Alibaba, and I'm a RISC-V process architecture designer. Today, I'm going to talk about our matrix extension proposal for AI applications on the RISC-V architecture. My talk including the following 3 parts. The first part is an overview of why we need to extend the matrix multiplan, and then our proposal on how we extend the RISC-V ISA to meet the application of AI. And the third part is a roadmap for future works. Okay, let's start. These slides are mainly about why we need matrix extension. Now in the AI domain, we can see matrix multiplan everywhere. So if RISC-V want to improve the performance of AI applications, we should add some extension to accelerate matrix operations. With this extension, we can get the following 4 advantages. The first is performance improvement. Matrix multiplan use 2-dimensional operations instead of 1-dimensional vector operations. According to the experience of other architecture, matrix extension can increase performance by 2 to 8 times. Secondly, it can reduce the memory bandwidth requirement. By matrix computation and data reuse, matrix extension can generate more operations with less memory access to save the bandwidth. And the matrix extension also reduces code size because the computing density of a single instruction increased. Finally, due to the high density computing and the domain-specific architecture, matrix extension provides us a low power option on the RISC-V architectures. Of course, other ISA developers have also noticed the advantage of matrix extension, so they have proposed their own suitable matrix extensions. For example, since ARM version 9 architecture, ARM proposed the scalar matrix extension. Intel released their advanced matrix extension on 2021. IBM also have their matrix multiplan extension in Power 10 architecture. In addition, we noticed that some RISC-V developers also trying to extend matrix operations on their own product, such as we found Sci-Fi. They add their intelligence extension to their new course X218. String Computing also share with us their attempts to extend the matrix operations or RISC-V. With these advantages and forerunners, RISC-V should have its own matrix extensions. Let's talk about the goal for the RISC-V AI matrix extension. First of all, the extension should aim to improve AI inference or training performance by accelerating matrix operations with vector extension or without vector extension. It can work together with vector extension, or it can work completely independent. In our opinion, matrix extension should be scalable and efficient to all reasonable design points, from small matrix processing unit to large matrix processing unit, whether the chip is designed for low cost or high performance, whether the microarchitecture is in order or out of order, whether the matrix unit is tightly coupled or decoupled. The matrix extension should work well. In addition to scalable, the extension should be binary code portable across all possible matrix register file sizes, just like vector extension. There should be no need to recompile or rewrite assembler or C intrinsic when register file size changes. Matrix extension should be an independent extension decoupled from vector extension. Vector extension. I will talk about it in more detail later because it's a hot topic among us. The extension supports multiple data types for AI training and for AI inference. In order to be more friendly for NN library and compilers, the extension should use uniform register files for not only source and dest registers, but also accumulator registers. The extension will also be easily extensible for future AI matrix extensions. Besides on the goal above, we propose a matrix extension for Xuantie RISC-V processors. One thing I want to mention is that this proposal is still under construction, and this is just an informal proposal. Let's discuss the relationship between matrix extension and vector extension first. Different companies have different solutions. SiFive choose to fully reuse the vector registers, while we see ARM choose to reuse the vector registers as its source operand and only extend the matrix accumulation registers, while Intel and string computing keep the vector registers and the matrix registers completely separated. What should we do in RISC-V architecture? We suggest the decoupling matrix extension from vector extension with the following considerations. Let's talk about the pros first. The tightly coupled structure means that the flops of matrix and the vector change proportionally. That is to say, the increase of matrix flops will lead to the increase of vector flops. The reduction of vector flops will also reduce the matrix flops at the same time. However, RISC-V architecture need to meet the requirement of different markets, not only in the scenario of supercomputing on automobile, but also the scenario of smart home or small household appliance. The flops of vector extension and matrix extension are not in proportional under all cases. Also, we found in some scenario, matrix and vector operations are required to perform instruction level parallelism, while some other case, matrix and vector operations can be performed serially. No binding flops relationship between vector and matrix is beneficial for RISC-V architecture to enter different market. And then from a developer aspect, developers no longer need to pay attention to register reuse issues, nor do they need to work hard to understand both vector extension and matrix extension to start network optimization. Independent matrix architecture is a kind of friendly architecture for software developers. And from hardware aspect, a complete separate programming mode is beneficial to better circuit implementation and simplify the process of timing or layout optimization. From a power aspect, both vector and matrix extension will generate a lot of power consumption. Decouple from vector can separate the heat of vector and matrix. Independent matrix architecture makes the thermal design of the chip easier. Of course, every coin has two sides. Independent matrix architecture also have some disadvantages, as we list on the right. The most frequent mentioned issues is that reuse can save hardware resources. However, it should be pointed out that it only works when the vector and the matrix flops match perfectly. As we can see, the vector flops of conventional RISC-V processor will greatly restrict the promotion of matrix flops. To reduce the waste of resources, we can adopt a way of reuse implementation. For example, a matrix processing unit can reuse vector resource at hardware implementation reuse level. Another issue is that the independent matrix architecture will increase the data transmission between matrix processing unit and vector processing unit. Independent matrix architecture only causes more data transmission when vector and matrix operation can be fused. Our profiling results show that proportion of this kind of operation is very small, and to avoid redundant data transmission, we also provide some matrix operations to cover requantification operations, which will always be fused in the extension. Because more register and status need to be saved and restored, the independent matrix architecture will bring more context switching cost. We have a solution to reduce the cost of context switching by introducing dirty flag, so as to only save the used registers. Consider attractive advantage of decoupling architecture. Our proposal will use an independent matrix processing unit without reusing vector registers. The data transfer between vector and matrix extension will use memory operations. As our proposal uses independent architecture, we have introduced the 8 two-dimensional uniform-sized registers. As like the slide shows, we have mlen. Mlen is the length in bits for each register rows. Mlen is the design time constant depending on the implementation of silicon vendors. The optional mlen you can be 128, 256, and even higher. Different mlen always means different flops. The silicon vendor can scale mlen to meet their computing needs. The matrix row is mlen divided 32. That is to say, when choosing 128 as mlen, a matrix register contains 4 times 4, 32-bit data. When choosing 256 as mlen, a matrix register contains 8 times 8, 32-bit data. Of course, we support different element-wise, such as 8-bit, 16-bit, 32-bit, and 64-bit. For the same mlen, if the mlen-wise is halved, the matrix row remain unchanged and the column are doubled. For example, when mlen equals 128, a matrix register contains 4 times 2, 64-bit element, or 4 times 4, 32-bit element, or 4 times 8, 16-bit element, or 4 times 16, 8-bit element. When the width of the element changed, our proposal always keeps the number of rows of the register unchanged. This will make it easy for software developer to understand and use our extension. Our proposal focuses on AI scenarios. The matrix multiplane and accumulation instruction are the core instruction of this extension. The extension has 2 instructions to support multiplane accumulation operations, one for integer and one for floating point. The way it works is shown on the left. Matrix A multiply matrix B and accumulate matrix C, and finally save the accumulated result back to matrix C. All the source operand and dest operand of this instruction use matrix registers, and no extra accumulation register are used in our extension. It should be pointed out that there are some suffixes that represent the data types by instructions. For example, for this integer instructions, S stands for signed, U stands for unsigned, B stands for 8-bit integers, H stands for 16-bit integers. By using suffix, the extension supports 8-bit integer, 16-bit integer, and half precision floating point, single precision floating point, and so on. In addition to matrix multiplane and accumulation, matrix memory access instructions are included to increase the bandwidth to match computation requirement. Matrix operations are also included to cover quantization and requantization operations in neural networks. This is a list of our extension instructions. Only 20+ matrix instructions are added. In general, we hope to provide the following features for AI matrix extensions. The first is scalability. By scalar mlen from 128 to 1024, and instruction execution cycle from 1 cycle to 64 cycle. Peak performance of the extension varies from 0.1 TOPS to 32 TOPS. The execution supports binary code portability. When mlen is changed, no rewrite or recompile is needed to execute binary code. We choose an independent architecture to decouple matrix extension from vector extension at programming mode level. But how to implement it is up to the silicon vendors. Also, the extension supports multiple data types, including integer 8, integer 16, gram floating 16, floating point 16, floating point 32, and so on. The extension also leaves rooms for future extension of other matrix operations, such as matrix transpose, and future data types such as integer 4 and floating point 8. We have open sourced our project on GitHub. In our open source project, we provide not only instruction set specification, but also software for extension simulation and evaluation. The software includes GCC and GDB as compiler and assembler. We also support matrix intrinsic in our toolchain. We provide a QMR quick emulator as a simulator to evaluate performance before silicon implementation. AI framework is also ready for the extension, including AI deployment toolkit and a neural network library. The picture on the right is an example of performance boost for different vector extension and matrix extension lengths for MobileNet and ResNet, VGG, and ULO. Of course, there are many details worth discussing about our matrix extension, but let's move on to talk about future works to make our extension more useful. AI applications are growing now, and recently nowadays ChatGPT has again brought more development to AI applications. We will continually extend the current matrix extension, including new data types such as integer 4, floating point 8, and the new operations as sparsity, pointwise, and transpose. Also, based on our current extension, we will provide more software ecosystem support, more neural network acceleration, more end-to-end demos, and AI frameworks and operating systems supported. Of course, we will also work on silicon implementation verification of the extension and provide capability test suite to help other silicon vendors to confirm that their silicon implementation meeting the extension criteria. That's all about our proposal. We're still on the early version of this matrix extension. I hope I made it clear what we want to do with this AI matrix extension. And please let me know if there is something wrong or perhaps we should do it in a different way. More details can be found on the GitHub. It's a T-Head GitHub or on RISC-V matrix extension spec. Thank you for listening, and I hope I have get enough time for question.
Okay, thank you, Qiujing. Okay, I think let's just jump into our main slide. And does anyone has any questions? Okay, I have some questions I want to discuss with you, Qiujing. Can you hear me?
Yeah.
Okay. First, I think all existing architectures for RISC-V already have vector acceleration instructions. Many researchers focus on that. And do you have any idea in what application will the matrix acceleration outperforms the vector acceleration, maybe in terms of power efficiency, or in terms of throughput, or in terms of performance? In what application will the matrix acceleration better perform? Do you think?
I think I give one slide about matrix operations in AIs. There are many matrix operations in AI applications, as shown in this table. All neural network models can be broken down into these implementations, and the three operations like direct convolution and Winograd and Gene are composed of matrix operations. If we use matrix extension to cover this, we can get more performance boost and power efficiency from this kind of matrix operations. And for the following tables, MAC operations account for a large percent of frequent used neural networks. Therefore, matrix extension, which accelerate MAC operations, can improve the performance of AI applications. And from the very beginning, we give some why we need matrix extensions. I have mentioned that matrix extensions have four advantages over vector operations in AI application. That is performance improvement, reduce memory bandwidth requirement, reduce binary code size, and lower energy. That's my answer.
I get it. Okay. My second question is, what model do you think will for multimodals? Because you mentioned the convolutional network and you mentioned the transformer. As you have mentioned the foundation model, such as GPT model, which is based on foundation model. Do you think the matrix acceleration will outperform the vector acceleration in terms of complex models such as transformer or GPT models? Because they work on huge number of matrix acceleration, huge volume of matrix operation. Will that give the matrix extension better performance than vector extension?
In my opinion, we think in that so big neural network such as GPT or transform, matrix operations, matrix extension should cooperate with vector extensions because there are too many kinds of operations in that neural network. So matrix extension will take the gene part or take the multiplane part, and the vector extension will take the such as pointwise part and reroute part or pooling part or attention part. So they can work together and they can boost the performance of this big neural network, in my opinion.
Okay, I get it. Does anyone have any questions? Okay, then I give just one more question. And you mentioned you have several extensions you want to support. Does your data, does the extension supports, do you have any priorities for implementations? How are the priorities chosen for data representation, data types?
Okay, yeah, our extension support many data types such as integer 8, integer 16, BF16, FP16, and FP32, but only integer 8 is mandatory. All other data types can be prioritized according to different application needs. For example, if the trip is using in training, you should FP32 and even FP64 will be first supported. If the trip is used in IoT devices, we use integer 8 as the only data type you need to support in the trip. Of course, if necessary, you can also give priority to extend new data types such as 14.8 and TensorFloat 32.
Okay, I get it. Thank you for the answer. And that's all my questions. Does anyone have any questions? Now is our, according to our agenda, it's our time to have this open floor discussion. Let's just, Qiujing, can you give the right to share the PowerPoint to me? And I'll go back to the main PowerPoint. And let's move to the next section. Okay. Okay.
Hello.
Hello. Okay. Okay. You can. Yeah. Question. You can. Yeah. You can ask. Okay.
Sorry, I can't hear it clearly. Can you? Yeah. Yeah. Thanks. Since VLAN and MLAN are different, we can the memory interface is departed by vector load store unit and matrix load store unit, and we have vector load store instruction and the matrix load store instruction. Our extension provides matrix load store to reduce memory bandwidth. Matrix memory access can load or store a two-dimensional matrix at one time. For example, matrix loader instruction will load multiple rows of continuous bytes, double words to matrix registers. The extension will that's how we depart VLAN and MLAN and how we depart the vector memory interface and the matrix memory interface. Yeah, and after if they are two, if they are almost the same, for example, 128 and 128, we will use as one interface. If they are too far away, for example, 62 and if one is 64, one is 522, 512. We will separate it apart.
Okay, Qiujing, I also still have a question. And you mentioned you have this matrix acceleration open source. What exactly is open source? Could we use the matrix acceleration RISC-V architecture to maybe run different models, maybe to examine whether any model or any application can perform on your code with maybe implemented on FPGA. And my question is, what is open source, and what can we do to use your open source code to demonstrate this, maybe to demonstrate and benchmark the performance of the matrix acceleration function?
Yeah, we open source our spec first, and then we open source our QMR, quick emulator. Other people can use QMR to evaluate our extensions performance. Actually, we have one demo about how to use our QMR to evaluate the ResNet performance. But we didn't give some FPGA resources because we have done it already. We will open source it later after we're done.
Okay, thank you.
Hi, can I ask a question as well, please?
Yeah.
Could you review the register file organization again for a brief moment? I'm trying to understand how much additional architectural state there is and how that would work for pre-operated operations.
You mean register file?
Yes, for the matrix.
Yeah. We have 8 register file matrix registers serve as a source register, destination register, and accumulation register. The register can be make 2-dimensional uniform size registers, both for source operand and accumulators. And if you choose MLAN, you choose the register size. For example, when MLAN is 128, the matrix register size is 4 plus 4, 32-bit element. 4 plus 4 element, which element is 32. And when MLAN equals 256, the matrix become 8 plus 8.
So these are
element.
necessarily square matrix registers.
Yeah. It's not square. It's because you
Oh, I see. Okay.
When the
Because of
element
the data
size
type.
is integer 8, it's not square.
I see. I see. Was there a requirement to fix it to this this 2-dimensionality, or would it make sense to consider 2 separate dimension specifiers? So MLAN for X dimension and MLAN for Y dimension. Is there a need to specify? Is there any advantage in specifying 2 separate M lengths for X and Y?
We choose to make it fixed because we choose to divide the MLAN by 32 for 2 reasons. One is because we want to speed up 8-bit multiplying 8-bit integer most. The accumulation data of this operation is 32, so we choose MLAN, and the row must be MLAN divided 32. Second, as we can see from this slide, as we can see from many slides, almost all the accumulator wise is 32 or 64-bit, no matter from ARM or Sci5 or IBM. I think they got 4 research before doing it, so we choose 32 as a divider, and so we fix the rest of the file size like this.
Okay, thank you.
I have a question regarding how the instruction works. So you now have matrices which have different dimensions, right? So can I treat any matrix registers as both A and B, like and do they get transposed? Because now you have an asymmetry in the dimensions of the matrices. So how does the matrix operation works on itself on these registers? And how does it accumulate on the final registers? Because the dimensions need to come together on the matrix multiply itself.
Sorry, I can't get your detailed ideas.
So, okay, let's look, for example, at the right-hand side. You have an 8-bit case for your matrix register, right? So you got a 4 by, how many do you have in there? 16?
Yeah, 16.
A 4 by 16, right? You have to multiply it by 16 by 4, and then your output is going to be a 4 by 4. If you're multiplying 2 of those matrix registers together, and you're going to get a matrix. How does the ISA handles the mismatches in the dimensions?
Sorry, I still can't understand.
So could you provide a definition of the matrix multiply ops as they are in the ISA, right? Do you have like some sort of description of what they take as an input, what they produce as an output?
Yeah. We have, for example, for this matrix matrix operations, like floating point, we have 4.4. 4 times 4 matrix and 4 times 4 matrix, and then get a 4 times 4. And if the is floating point 6, we will have 4 times 16 and 16 times 4 times 16 and 16 times 4 to get a 4 times 4 element result matrix.
So does that mean you only support two types of matrix in terms of size? Only 4x4 times 4x4 and all 4x4 and 4x16?
We have tail operations because if the size is not the right size, you want to full cover the extension matrix registers, you can have tail operations. You can say we want to have size 2 times 2, 3 and times 2 to get a 2 times 2 matrix. It's okay, but you can't full use of the matrix registers, and you will lose some performance.
So if the matrix is larger than 4x4, you split it, and when it's smaller, you will lose some efficiency. Is that right?
Yeah.
Okay, I see.
So can I piggyback on that question, right? The case where we looked at the matrix, right? The integer 8 case, we only have 4 rows, but we have 16, right? So how do we take the full throughput when multiplying something which is 4 by 16? You would have to have a 16 by 4 matrix. Do you allow transposes, for example, in the matrix multiply to fully utilize the 2 matrices? Because otherwise you have redundant space in the matrix storage, which is rather expensive in general because it grows with the square of the size.
Yeah, we should divide the matrix, the big matrix into this small matrix, just the right side. If at the end or at the end of the line and the rows, you should use the tail operations to cover the small part of the leaf part of the matrix.
Mhm. Okay. Does anyone has any other questions? Okay, I think we still have 20 minutes.
Any support for convolution in future works? Is there any plan?
No, we just use image to colon to support gene, and to support convolution. We don't have any, because we think convolution is too big for CPU to process.
How do you support image to call? Do you support it externally? So is it like the CPU that needs to do it, or?
We use software to do image to colon, and then we use matrix extension to calculate the other multiplication. We use software and a vector extension to do the image to colon.
Okay, that's the typical approach. The reason for asking is that if you do im to call, you have a large factory memory expansion. So you have to do from whatever you need to convolve, you need to expand into memory. There's going to be like a 4 or 5x expansion in terms of size. And then you have to read it back from memory and then process it. And usually there's some engines out there, some neural network engines, they do that on the fly and they avoid reading and writing the memory and cause that expansion.
Yeah, but in CPU, image to colon ASIC unit is too big, and we can use vector extension and matrix extension parallel them to do the both of things at the same time. So I don't think you lose too much performance. Of course, it lose memory. We need big memory to support this kind of operations.
So do you have any communication between your matrix registers and your vector registers? Any way of just communication without going through memory, through loads and stores?
We just do it through road stores because we think make some connection between matrix vector, matrix operation and registers and vector registers is too difficult for physical implementation. We have tried, but we found out that cost too much resources to do this. And if we do this in memory operations, it isn't the bottleneck for our application performance boost. So we choose to remove the vector register connection with matrix registers in our extension.
I think I would have, I would like to see, a vector interaction with matrix first. So if you could use 2 vector input registers to do an outer product type operation to a matrix destination register, that would have been quite interesting.
Yeah. Yeah, should I give back the right to show the PowerPoint to give back the right to you, Mr. Zhou?
Okay, so if no one has any other questions, I think we'll just end our meeting today. Thanks for Mr. Qiu for your sharing your proposal, and thanks for your contribution to the RISC-V Society. And I think we will end today. Okay, so we still have 10 minutes. And if no one has any questions, then we will continue. We will end our meeting today, and we'll send the minutes to everybody. And if anyone has any other questions, I think it's more appropriate to discuss offline. And anyone has any other questions you want to send to me, I'm glad to discuss with you guys. Okay, so no one has any questions? Okay, that's it for today. Thanks for everyone. Thank you, everyone. Thank you, Qiu.